The nearest star system to our own, Alpha Centauri, sits approximately 4.37 light-years from Earth. Using the fastest spacecraft humanity has ever built, the Parker Solar Probe, which set a velocity record while diving close to the Sun, a journey to Alpha Centauri at that probe's peak speed would take roughly 6,000 years. Voyager 1, the most distant human-made object, traveling at about 17 kilometers per second, would need over 70,000 years to cover the same distance, if it were even pointed in that direction. Breakthrough Starshot, announced in 2016 and backed by an initial $100 million research commitment from the Breakthrough Initiatives organization founded by Yuri Milner, with public support and advisory involvement for physicists, including the late Stephen Hawking, proposes a method that could make the trip in approximately 20 years of flight time instead of millennia. The proposal does not involve building a faster rocket. It involves abandoning rockets almost entirely in favor of a method of propulsion that uses no onboard fuel at all. The fundamental problem with chemical rockets for interstellar travel is the rocket equation itself, the mathematical relationship, first formalized by Konstantin Tsiolkovsky, that governs how much fuel a rocket needs to reach a given velocity. Chemical rockets must carry their own propellant, and accelerating the propellant to high speed requires more propellant, which itself must be accelerated in a compounding relationship that makes velocities anywhere close to a meaningful fraction of light speed essentially unreachable through chemical propulsion, regardless of how much fuel mass is allocated. Even the most efficient conceivable chemical rocket, built with the entire mass of the solar system as fuel, could not approach speeds that would make an interstellar crossing survivable within a human lifetime. Breakthrough Starshot's solution is to leave the engine on Earth, rather than carrying propulsion mass aboard the spacecraft. The project proposes generating thrust by shining an enormously powerful, precisely focused laser beam at a lightweight reflective sail attached to the spacecraft. Photons, particles of light, carry momentum despite having no mass, and when light reflects off a surface, it transfers a small amount of that momentum to the surface. This is the principle behind solar sails, which have already been demonstrated in space using sunlight, including Japan's Ikaros mission in 2010 and the Planetary Society's light sail missions. The momentum transferred by ordinary sunlight is tiny. To accelerate a spacecraft to a meaningful fraction of light speed within a reasonable distance from Earth, you need light vastly more intense and more sustained than anything sunlight can deliver at interplanetary distances. This is where the project's central engineering proposal comes in. A ground-based or near-Earth laser array with a combined output of approximately 100 gigawatts, focused with extreme precision onto a sail only a few meters across, for a period of a few minutes. The spacecraft itself, in the Starshot design, is almost absurdly minimal by the standards of conventional space exploration. The nanocraft, officially designated Starship in early conceptual designs, is envisioned as a wafer-scale device weighing only a few grams, integrating a camera, photon thrusters for altitude control, a power supply, navigation and communication equipment, all etched onto or attached to a chip roughly the size of a postage stamp. This gram-scale mass is not an incidental design choice, it is the entire point. The physics of light sail propulsion makes the achievable acceleration directly dependent on the ratio between the sail's area, which determines how much light can be captured, and the total mass of the sail and payload system, which determines how much that capture momentum must accelerate. A heavier payload requires proportionally more laser energy to achieve the same velocity, and the 100 gigawatt laser array Starshot proposes is already, by a wide margin, beyond any laser system that has ever been built. Existing high-power laser arrays used in fusion research, such as the National Ignition Facility, operate at a small fraction of this power and only for fractions of a second, not the sustained multi-minute pulse Starshot's mission profile requires. Scaling the spacecraft up to anything resembling a human crewed mission, or even a substantially larger robotic probe, would require laser power increases that are not currently considered achievable with any known or near-term technology. The gram-scale nanocraft is the compromise that makes the propulsion physics work within the bounds of plausible, if still extraordinarily ambitious, near-future engineering. The sail itself, attached to the star chip, is proposed as an ultra-thin, ultra-lightweight reflective material only a few hundred atoms thick, with an area of several square meters, engineered to reflect as close to 100% of the incoming laser light as possible while surviving the intense thermal and mechanical stresses of the acceleration phase. The acceleration phase itself is the most extreme and most technically demanding component of the entire mission profile. The laser array would focus its combined 100 gigawatts of power onto the sail for a period of only a few minutes. Current mission designs suggest approximately 10 minutes, during which the nanocraft would accelerate from rest to approximately 20% of the speed of light. This acceleration profile implies forces on the sail and chip that are significant, but, according to the project's engineering analysis, survivable for a sufficiently robust, simple design without complex moving parts or fragile components, given the extremely low mass involved. 20% of the speed of light is approximately 60,000 kilometers per second, fast enough that the spacecraft would cross the average distance between the Earth and the Moon in about 6 seconds. At this velocity, the 4.37 light-year distance to Alpha Centauri would be covered in approximately 20 to 25 years, depending on the final achieved velocity and the specific trajectory flown. The precision required to focus a 100-gigawatt laser array onto a target only a few meters across, located at a distance that grows from 0 to many millions of kilometers over the course of the several-minute acceleration burn, represents an optical and engineering challenge with no current precedent at this scale. The laser array itself would need to consist of many thousands or millions of individual laser emitters, phase-locked together with extraordinary precision, so that their combined output behaves, in terms of beam coherence and focus, as a single enormously powerful and tightly controlled beam, a technique called phased array beam combining, which has been demonstrated at much smaller scales in laboratory and limited field settings, but never at anything approaching the scale or power Starshot's mission would require. The challenges facing breakthrough Starshot are not limited to the laser array and the acceleration physics, though these represent the most fundamental and widely discussed obstacles. Several additional engineering problems remain substantially unsolved. The sail material itself must satisfy a set of requirements that are in significant tension with each other. It must be extremely lightweight to minimize the mass that must be accelerated. It must be extremely reflective to maximize the momentum transfer efficiency and to avoid absorbing laser energy as heat, which could destroy the sail. And it must be structurally robust enough to survive the acceleration forces and the years of subsequent interstellar transit, during which it will be exposed to cosmic radiation, micrometeorite impacts, and the extreme cold of deep space. Materials science research into candidate sail materials, including various metamaterial and dielectric mirror designs, has been an active area of the project's research funding, but no material meeting all of these requirements simultaneously has yet been demonstrated at the scale and performance level the mission requires. The navigation and communication problem is similarly unresolved at the engineering level required for a real mission. A gram-scale spacecraft traveling at 60,000 kilometers per second past the Alpha Centauri system would have only a brief window, likely measured in hours, during which its onboard cameras and sensors could capture useful data about any planets in the system, including the potentially habitable exoplanet Proxima Centauri b, discovered in 2016 orbiting the nearest individual star in the Alpha Centauri system, transmitting that data back to Earth across 4.37 light-years, using a power source and antenna that must also fit within the gram-scale mass budget, is an open problem that has not been solved with any currently demonstrated technology. Signal strength falls off with the square of distance, and a transmitter small and light enough to ride on a gram-scale chip would need to somehow generate a signal detectable across an interstellar distance using extremely limited power. The targeting and dispersion problem during the long cruise phase is also significant. A swarm of nanocraft, launched to maximize the probability that at least some survive the journey and arrive with functioning systems, would need to maintain enough trajectory precision over 20-plus years of travel through the interstellar medium, which, while extremely sparse, still contains dust and gas particles that could damage or destroy a sail and ship traveling at relativistic speed to actually pass close enough to the target system to gather useful data. The atmospheric interference problem affecting any ground-based laser array of this scale has led many in the Starshot research community to favor locating the laser array at a high-altitude site, or potentially in space, though a space-based array of the scale required introduces its own substantial set of engineering and cost challenges, including the difficulty of constructing, powering, and maintaining a structure of this size and power output outside Earth's atmosphere. The funding and engineering timeline for Breakthrough Starshot remains explicitly long-term and research stage. The project's publicly stated ambition has been to develop the foundational technologies, phased laser arrays, lightweight sail materials, gram-scale spacecraft electronics, over a period of decades, with an actual launch attempt not anticipated before the most optimistic estimates place it several decades in the future, and more conservative assessments suggesting a much longer horizon given the scale of unsolved engineering problems. Despite these substantial obstacles, the project has continued to attract serious scientific engagement, including peer-reviewed research collaborations with academic institutions and national laboratories investigating specific subproblems. Laser phasing techniques, sail material science, and the astrodynamics of relativistic speed interstellar trajectories. The project's significance lies not necessarily in a confident prediction that it will succeed on its proposed timeline, but in its function as a serious, physics-grounded research program forcing concentrated investigation into engineering problems that any future interstellar mission, regardless of the specific propulsion method eventually used, will likely need to address in some form. The core appeal of the Starshot concept, distinguishing it from most other speculative interstellar travel proposals, is that it does not require any physics beyond what is already well understood and experimentally confirmed. It does not depend on speculative propulsion concepts like fusion rockets, antimatter engines, or theoretical exotic matter warp drives, all of which require either physics not yet demonstrated to exist or engineering capabilities far beyond anything currently conceivable. Light sail propulsion using powerful lasers is a direct application of well-established electromagnetic physics, the same physics in simplified form that explains why a comet's tail is pushed away from the sun by solar radiation pressure. What Starshot requires is not new physics, but engineering at a scale and precision that has never been attempted. Lasers more powerful and more precisely phased than any built, sail materials thinner and more reflective than any manufactured, and spacecraft electronics miniaturized and hardened beyond current standards, all of which must function correctly, without any possibility of repair or adjustment. For a mission spanning more than 2 decades across a distance no human-made object has ever approached. Whether these specific engineering problems are solved within the coming decades, or whether some other propulsion approach eventually achieves what Starshot envisions, the project has reframed a question that for most of human history existed only in the domain of science fiction. Not whether a probe could ever reach another star system within a human lifetime, but specifically what combination of laser power, sail mass, and material science would be required to make it possible, and how close. Current technology already comes to assembling the pieces,